This lecture, we're talking about Markov decision processes, or MDPs. And before I go into code, I want to give an explicit, detailed description of what an MDP is and give you an example of one so you have this intuition in mind before you see code. So what is an MDP? A Markov decision process, or an MDP, is a problem formulation that defines how an agent takes sequential actions from a state in some environment, and it's guided by rewards. And this uses uncertainty in how it transitions from state to state. And it's called Markov because it only relies on the current state and it transitions to some future state. So there's no memory of all of the past states. And this allows this problem formulation to be applied much more broadly. So more formally, an MDP is defined by the following things. So don't let the notation scare you, but the idea is we have some state space of all the possible states that the agent in this environment can be in. And I'll give a concrete example in the next slide. We talk about all the actions or the action space that some agent could take. What is the probability of transitioning from one state to the next given the current state and an action? This is called the transition function. We talk about the reward function, which is kind of the core of MDPs, and how when you solve it, it's trying to maximize this discounted reward over time, which leads me to the next thing, which is the discount factor, which is a mechanism to control how myopic or short-sighted your agent is in receiving rewards, or whether it's going to wait for future rewards to come. And so a heavy reminder here that an MDP is a problem formulation and it's not an algorithm. An MDP formulation enables the use of solution methods, which we would call algorithms. So now I'm going to detail an example MDP, which I always love to fall back on, called the grid world. So in the grid world, there's an agent here shown in yellow that moves around a grid attempting to collect as much reward in the green cells as possible, while avoiding negative rewards shown in the red cells. And so the state space for this problem is defined as the set of all possible states an agent can be in. This could be discrete, meaning there's a finite number of states, like this problem, or continuous, meaning there's an infinite number of states. So as an example for the grid world problem, all possible XY value cells in this grid, which is a 10 by 10 grid, those are all the states. So in this case, the state space has 100 discrete states in its set. And as an example, pointed here in yellow, this is the state of over 9 and up 7. An action space is defined as the set of all possible actions an agent can take. Again, this could be discrete or continuous. So for the grid world example, as you see laid out on the grid, there are 4 discrete actions which associate to the cardinal directions of up, down, left, or right. So when an agent is in one of these cells or one of these states, the action it takes is shown here in the illustration. So as an example, you want to take action down when you're in state 9-4 because there's a heavy green reward there. Now, the transition function, or sometimes called the transition model, defines how the agent transitions from the current state S to the next state S prime when taking some action A. And so what this is this returns a probability distribution. So it's a distribution over all possible next states S prime, given the input of the current state and current action. And as an example, in the grid world problem, there are stochastic transitions, which means it incorporates randomness or uncertainty. And so as an example, if you look here on the right, if the agent is in that state S in the middle and its action is to go up, there's a 70% chance that it transitions correctly to that next state of where it's highlighted 0.7. But there's actually a 10% chance in each direction to transition to a different state, which is the uncertainty of the movement of the agent and how we can bake it into the problem there. So really there's only a 70% chance it's going to correctly transition and a 30% chance that it transitions incorrectly. In other words, a different action is taken. And so the reward function for an MDP is defines the reward an agent receives when taking some action A from state S. And in this particular example, there are 2 cells shown in green with positive reward of 10 and 3, and there are 2 cells shown in red with some negative rewards shown or as -5 and -10. All other cells have a reward of 0. And this is sometimes called the reward model. Now, the discount factor controls how myopic or short-sighted the agent is in its decision-making. So when gamma, the discount factor, which lies between 0 and 1, and it's a real number, when it's 0, which you see all the way on the left, the agent only cares about some immediate rewards. So this reward really isn't spread to kind of other states, and I'll get to what I mean about reward spread here. And so it's myopic here. It's really short-sighted. But as gamma approaches 1, you can see as the value gets larger, the agent takes in more potential future information in its decision-making process. If gamma is all the way 1, then it's kind of dominated by the future reward. As you can see, all the cells are the same color green, as opposed to kind of some gradient to lead you to some better future states. And just a little quick peek into the code. This code on the left defines the entire grid world problem that I just described using the QuickPOMDPs package. So this is just a sneak peek, but we'll walk through this in more detail in the Pluto notebooks. And you can copy and paste this into your own notebook or a REPL, and you'll be able to play around with this MDP here. And so there are a number of ways to solve MDPs, which I'll talk about in the notebook. Here we split them up between whether or not they can handle discrete state spaces, meaning there's finite number of states like the grid world problem, or continuous state spaces and action spaces where there's infinite number of states the agent could possibly be in, which makes the problem much harder. So here are 4 examples of MDP solution methods and their associated Julia packages. And it's very important and I'm going to dwell on this, it's very important to pick the right solver for your specific problem. If you have discrete states or discrete actions, you are limited in what you can do. Same with continuous spaces. So you want to be very deliberate in what solver you're attempting to use. Also, certain problems are better suited in the reinforcement learning domain. So there are several reinforcement learning solvers that adhere to the POMDPs interface. Things like tabular TD learning, which includes algorithms such as Q-learning or SARSA lambda. And then there's some deep RL packages like deep Q-learning and Crux, which can handle continuous state and continuous action spaces. And they implement some more cutting edge algorithms in the deep RL field. Okay, now we get to the fun part where I detail the MDP formulation for the grid world problem in an interactive Pluto notebook. And if you haven't heard of Pluto before, I recommend watching the 2020 JuliaCon video by Fons Vanderplas that details an engaging presentation on the introduction of Pluto and how it's different from notebooks like Jupyter. So breakdown here is I'm going to explain the grid world problem and how it fits into how you can define it in Julia code. And then I'll talk about solution methods, both online and offline, and how to run simulators and some nice visualizations in between. So as described before, an MDP consists of this 5-tuple, which really consists of the state space of all possible states, the action space of all possible actions, your transition function, your reward function, and some discount factor. And in this case, for the grid world problem, the states and actions are discrete. So for our problem, we use POMDPs for this MDP type, POMDP model tools we use for the sparse categorical distribution. POMDP policies will give us some policy types that we can kind of do some multiple dispatch on. QuickPOMDPs, which is one of my favorites, is a way to succinctly describe and set up a MDP or POMDP, and we use that heavily here. And also I plot in a LaTeX style just because I'm biased towards LaTeX. So first, let's set up the environment. So just some things that we want to kind of get out of the way is some parameters of our environment. So we have the size of the grid, which is a 10 by 10 grid here. And then we also have some null state, which is a terminal state outside of the grid. So when you go into one of these green or red states, you get the reward and then transition to this null state, which is just somewhere outside of the grid. Details really aren't important here. But what's really important is the probability of transitioning. So this is the probability that we transition to the correct next state. And this is really what adds uncertainty into this environment when we're moving an agent around. And so we first set up these parameters, and you can see the grid world here that we can render with the code that's hidden above. So to define the states, we just simply make a struct that includes the x and y integer values of this 10 by 10 grid. The state space itself actually consists of all xy pairs in this 10 by 10 grid, including the null state. So if you look here, you can see all of the states, including this last null state, and there's 101 values in here. And for those who are unfamiliar, this script S in Pluto can be typed by /src and then hitting tab. And you'll see it change to the script S. Note we also defined the equals function to compare two states just based on their x and y values, just for convenience later. So now the actions. So the actions, which we detailed before, are up, down, left, and right. So discrete number of actions. We use Julia's built-in enum just to have some nice action type we can later refer to. And so the action space itself, which is this script A, is the set of all actions, all 4 of these actions. And we include some helper code here just to define what it means to take an action. So like, the action up just changes your y value up 1. And so that's what this is defined here. And then we can add 2 states, and this allows us to kind of do some convenient stuff in the transitioning function later, which is what I'll get to next. So the transition function returns the dynamics, or rather it's the dynamics of the agent in the world. And so what it does is it returns a distribution over all possible next states. So to go into a little bit of detail, the transition function T here takes as input some state and some action. And in our case, for this problem, if the reward is non-zero, meaning we're at some reward or negative reward state, we're going to deterministically transition to the null state. So at that point, we're kind of out of, we're going to transition out of the environment. But in general, what we want to do is we want to calculate what is the probability of, transitioning up, which we know is, or transitioning to the correct state, which we know is P transition here. And then we want to fill a distribution, which is a categorical distribution, meaning there's some probability to transition to the state that's defined by an action, or to the state left of us, the state below us, or state to the right of us. So what this code does, as succinctly as possible, is to encode that transition. And in here, we have some kind of handling of whether or not we're going to transition to a wall. And if we do, then we bounce back to our current state. And then we just return what's called a sparse categorical distribution, which for every possible next state here, which is just a set of all possible next states, there is some probability mass associated to that next state, and all of these probabilities sum to 1. And I'll show a little bit more details later. And so we just define this inbounds function given a state, so we know, okay, that this agent is correctly in the grid. Now for the reward function, sometimes you can see it as just taking in a state or a state action, or even a state action and next state to compute the reward. Really, in our case, we're really worried about just state. So this defines the reward for each of these individual cells. So you can see each of these cells is associated with some reward that we see in just these conditionals here. And then the discount factor. So in our case, we're going to use 0.95, which is a commonly used value. And so what this does is kind of spread out the future discounted reward to states with a nice gradient that allows for some learning algorithms to really find some optimal policy here. And we can play around here with how this discount affects the spread of this reward as we go down to 0. You'll see that the reward is really not spread as much In this case, I'm saying reward, but we'll talk about a term called utility or value, which is this, the sum of the discounted future rewards from a particular state. So we go all the way down to 0. We see that the agent is myopic, meaning it just cares about that next state. And so really, there's not a good way to try to figure out what is the best policy from, say, that top left corner state, this 10 over 1 up 10, what to do. But as we slide it over, we have kind of more of a gradient that leads us to this high reward terminal state. And then the next thing too, which leads me, is termination. So when an agent is in this null state that's outside the grid, which we arbitrarily define, then we say that the game is over, the environment stopped. Sometimes it's called an episode, where an agent is running around, or rather moving around its environment, and we say, okay, it stops when we get some reward and we go to this terminal state outside of the grid. And so all of that together, we can define the MDP here using QuickPOMDPs. So we set up this abstract type called grid world, which we say it's an MDP that takes in the state type and action type that we defined above. And then we define the MDP in this really concise manner, where we just define the state space, the action space, the transition function, reward function, the discount, the initial state, which we just say can be sampled from the full state space, the termination function, which defines are we in a termination state, and some render function that we can use later to render the actual grid. So now that we've defined the MDP for our grid world, we can try to solve it. And when we say solve, this means we want to produce what we call a policy. So this means for any particular state, we want to get back an action to take in that state. What is our policy? And so really a policy, sometimes it's called pi, or it's the symbol pi, is a mapping from states to actions. And so typically in the POMDPs.jl interface syntax, you have some algorithm that is the solver itself, and the inputs to this algorithm, or into this constructor, are the parameters of the algorithm. And then you call solve, given that solver, and you pass in the problem itself, the MDP in this case, and it will return back that policy that I just described. One algorithm we can use to solve discrete MDPs is called value iteration. Value iteration uses dynamic programming and the Bellman equation to compute the optimal value or utility you start iteratively. So don't be too discouraged if you don't understand everything in this equation. I'll walk you through it, but what this is doing is for all states S, we're trying to compute what we call the optimal value or optimal utility of a particular state. So really what that means is we want to, over all possible actions we can take, we want to maximize both our immediate reward by taking, that particular action from our state, but also what we call the discounted future sum of rewards. So this discounts by gamma all possible future states, or rather all possible future rewards we could get. And it's recursive here because we're calling U star, and this is where the dynamic programming is very helpful. And so from this optimal utility, we can actually pull out an optimal policy that's extracted from this using an argument max. And again, this is just to say what action A produced the highest utility for this particular state. But of course, we don't actually have to implement these algorithms ourselves. We can use POMDPs.jl. In this case, there's the discrete value iteration package that implements value iteration for us, particularly for discrete MDPs. So an important note is value iteration is model-based, meaning it relies on the transition model and the reward model directly. And so what we can do is first we set up our solver. So the value iteration solver, we're going to say run for maximum iterations of 30. And then what we can do is actually produce a policy. So we call solve given that solver in an MDP. And this really is a table that associates for any particular state maps to an action. So you can see from state 1, go right. That's the optimal action that this found. Again, a policy pi takes in some state and spits back an action. Takes in some state and spits back an action. What we can do too is kind of get an example of the transition probability of these states. And what we can also see is just plot this optimal policy on top of the grid. So what I'm showing here on the left is called a policy plot. So for the entire grid world, you'll see an action to take, and this action is produced by value iteration. Right now, we can move around the agent in this world. We're currently at this blue highlighted box, and we can see, okay, what is the probability of transitioning to all the possible next states? And those would be the cardinal directions and the state you're currently in case you hit a wall. So you can see from this, the action to take, from the state, the action to take would be go right into this reward state here at 9,3. And so there's a 70% chance that we'll actually transition there. And the distribution shows there's a 10% chance we'll transition to these other neighboring states that's around us. What's also cool is you can actually see the value, or the Q value, which is often refers to the state action value. So this is, don't maximize over all actions, just give me the value of, say, taking a particular action. We can see, what are the values of those actions here, and then we can see, is it selected by the policy here. We can move this around, so if we want to see, okay, if we are moving up, say, to this particular state, what is the probability of transitioning kind of to the states around us? We can also move to the walls, and you'll see that as we move to the walls, there's a higher likely or a more probability mass put on the fact that we're going to transition back to the same state because we kind of bounce to these two directions. And then there's some likelihood that we're going to bounce to these other two neighboring states here. And we can also see that if we put directly into, say, one of these actual reward states, we just transition back with probability 1 to a terminal state that is what we call the null state outside here. And that's just particular to this problem. What we can also do is call the transition function directly, given some state in action, and actually get back a distribution using the Unicode plots that shows us, where does the probability mass lie in all the next potential, or rather next possible future states. So you see here, if we take action right in this case, then there's a 70% chance we will correctly go right, and then there's a 10% chance for each of these other cardinal direction states, and a 0% chance of transitioning to the current state you see is 8,3 because we're not near a wall. An example using the policy directly, again, given some current state S and some policy pi, we can map that to an action, and it just pulls out an action that we learned in this case through value iteration. And so we can query this policy using the action function. So it takes in a policy, current state, and it spits back an action. In this case, the action is right. We can also look at the value or the utility of a particular state. So the value of this state given the policy is about 9. And really the way that is computed, I've shown up here, is it maximizes over all of these. Since you're just giving it a state as input, it maximizes over all these, and it'll spit back the one with the maximum value here. And so to go a little bit more into detail there, so I've talked about a Q value, which really is a state action value as opposed to just a state value. And so it incorporates the immediate reward with the discounted sum of future rewards. And so there are two functions you can call, either value given some policy and this current state, and this gives you back the utility, just that particular state. Or you could call value given both the state and an action, which we would call a Q value or sometimes state action value, really where this utility is just described as the maximum value over Q when you look at all of the individual discrete actions. And so here I just show, I just for convenience redefine it to Q, which is just the value given some policy in a state action. The utility, which I'm just showing this as a means of comparison, where it's, you maximize over all possible actions of our MDP, which you can call actions to get the full action space. You maximize this Q value, and just, for posterity's sake, this U is really the same as calling, the provided value function given some state. So next, I want to show some visualizations of the policy and, kind of tweaking some of the parameters to understand how they work. So I have a plot grid world function that I defined above in a hidden cell. Feel free to look at it when you have the notebook yourself. But first, I just create I recreate the MDP using QuickPOMDPs, just so I have one I can play around with here. I resolve it using the value iteration solver with some number of iterations that I can control down here with a slider. And also I just solve this policy, again, just to get me this optimal policy that I can play around with here. So if I render this, you'll see, okay, if we haven't done any value iteration iterations itself. And what this means is it just picks the default action, which happens to be the first action, which is up. So for every cell, doesn't know what to do, just go up. As we increase the iterations, you can start to see how the value iteration algorithm works. It's really starting to, for lack of a better term, spread the reward using the concept of utility through the other states. And as we increase the iterations, you can see the states that are further away from those reward states start to now get this information from future states that have kind of iteratively got to it. And after a while, you'll see it starts to converge. And really, value iteration here is converging to the optimal policy. This is the best policy, given the fact that transitioning is uncertain with that 70% chance of transitioning. This is, for every state, the best action to take and lead you to the highest reward area. And you can see some of these around here are, colored a little differently because there is some probability, given, namely 10% chance that you will accidentally transition to this negative reward state. So that's why around these cells you can kind of see a little different shaded green. Yeah. We can also do is play around, like I've shown before, with the discount. So as we discount this, it's again starting to kind of reduce the future spread of information. And so the higher the discount, the more future information you're taking in, whereas a discount of 1 is saying, okay, from this state, I know I will get to this extremely high reward state. So all of these are the same color, but right around these red states, you can see the colors are a little different because there's some likelihood that I'm going to transition. But from up here, you can skip all the way around any of the likelihood of transitioning to these negative reward states. You can also save these plots using the plots package, which is really nice to save this as, say, like an SVG. So here I'm showing an animated GIF using the real package, which you can see the code hidden under here. But what this is doing is it's just exactly what I did, cycling the number of iterations for value iteration. You can start to see the spread of this reward over time, and then it converged to some optimal policy towards the end. And I also show the same thing, but just iteratively changing the gamma value, that discount value. So you can really see, as we change that value, how that reward is spreading into utility of these states, but also how the policy starts to change to really point towards that high reward area. And now let's talk a little bit about reinforcement learning and reinforcement learning solvers. So the domain of reinforcement learning is a little bit different than what I just showed with value iteration. It still relies on the problem to be defined as an MDP most of the case. But in this case, the agent is interacting with the environment as opposed to value iteration, which I show, which technically is a planning algorithm, but the differences are somewhat pedantic. Value iteration isn't letting the agent experience the environment itself. It's actually just looping over all possible states and all possible actions and iteratively using dynamic programming, coming up with the optimal value. In RL, in reinforcement learning, the idea is that the agent, takes some action that affects the environment and gets some observation about what happened because of that action. So it's this interactive loop of experience exactly in the environment as opposed to the exhaustive access to the full state space or action space. So a certain set of algorithms that fall under the reinforcement learning umbrella are called temporal difference learning algorithms, or TD learning algorithms. What this really means is, so they're model-free reinforcement learning algorithms. When I mean model-free, I mean they don't use the transition model and the reward model directly. They just deal with experience of, actually sampling something from the environment itself. One of these algorithms, called Q-learning, is an example of this model-free approach. And what you see here is there's no T or R in this, the functions capital T or capital R in this equation. And what this is trying to do is it's trying to, through experience, update, and that's what this arrow indicates, update your state action value or utility given your old value, some learning rate of how quickly or how slowly we want to learn from change, the immediate reward that you get from actually interacting with the environment, some discount factor gamma that we've introduced before. Then you get this recursive call to the future state estimate that we're going to maximize over all next possible actions. And you subtract that from your old value. And what this entire thing is called is this temporal difference, where we have some target value we're trying to reach, and there's the current value. And so we see what, is there a better action by maximizing over all possible ones compared to the current action that we're evaluating. And so for Q-learning, we're going to set up, again, the MDP. We're going to set up the Q-learning solver, which comes from this tabular TD learning package. And we set up some parameters, the learning rate. There's an exploration policy, which provides some randomness to what actions it's going to explore. And also, we can then directly solve this, again, with the solve interface function. And what you see is it's not as clean or optimal as value iteration, and because Q-learning isn't intended to be. Value iteration is really useful on small MDPs with discrete state and action spaces that are relatively small, not extremely large, because it's going to iteratively use dynamic programming to actually solve for a true optimal policy. In this case, Q-learning, which is in the reinforcement learning setting, is actually just learning through experience. And so as we can change this value down to 0, and initially, it doesn't have any information on, what state information to, all the utility is 0 here. And as we start to slowly change this, we start at some random initial state, we get some experience, we update our Q value estimates, and over time we can start to see that the more iterations that we give it, the more information starts to update, and the better that this policy is actually going to perform. And then we can see more green is really being spread. Again, it takes many more iterations than value iteration because it's less restrictive, meaning we don't really need the reward and the transition model directly. We just need to be able to sample, some transition in the environment in a different manner. And so as this starts to go up, we can start to see, these values really starting to spread out. and we get a fairly decent policy towards the end where, it can kind of get confused as to where to go because, again, this isn't going to be optimal. It's just approximately optimal, but we still get some good policy at the end. The next algorithm that we show here is called SARSA, which is a modification of Q-learning, so it's also model-free. And it uses the state action reward next state next action tuple, which is why it's called SARSA. So it uses the actual next state A prime to update the Q values instead of maximizing over all of the actions. So you see here there's no more max over A prime. We actually have to experience what is the next action that we would have taken so we can get this target value to compare with our existing value. And so again, what we can do is set up some MDP, call this SARSA solver given some particular parameters of this solver, and then solve for a SARSA policy. And again, it's not going to be optimal because it's relying on experience with random initializations to build up a policy over time. The more iterations you give, generally the better the policy will be, but there's no guarantees with these TD learning type algorithms relative to kind of your value iteration planning type algorithms. What I wanted to mention here is that the algorithms I just presented, both value iteration, Q-learning, SARSA, these are offline solvers. What I mean by offline is that it's going to compute some policy, do a lot of computation, and then give you something that you can look up, given a state, spit back an action. So it's going to do that, quote unquote, offline. And then when you actually need to employ this policy, you have this static policy that you just look up what's the best action to take from my current state. Switching gears a bit to online solvers, instead of computing this table or this function that we can use to look up, we will run the algorithm in real time when we need to know what action to take. This is generally useful for really large state spaces and large action spaces. In the grid world problem, it's kind of inappropriate in a way, but it's also just not the best algorithm to choose here. But this is still a good illustration of how to use it. So in the online setting, when we're just given one state, our current state, and we want to say what's the next action to take. And usually this means it's going to run some computation and spit back some action for you to take. In the case here, we are introducing the Monte Carlo tree search algorithm that's through the MCTS package. And what it'll do is it's going to kind of simulate or hallucinate these future rollouts of a policy, which really means it's just going to play out kind of future experience to try to estimate, okay, if I'm in this particular state and I take this action, what is the value of that? And it's going to do this over time and go through each of these 4 steps here to build out this search tree. And it's called an anytime algorithm, which means that at any point in the computation when it's running, you can stop it and you can get back, what is the best action from my current state, which we would see here as the top node. What's the best action to take? Once you take that action, you transition, in real time to the next state. You do all this over again. You recompute the tree from scratch, starting at a new root node. And so here we'll just set up the MDP. We'll solve that MDP using MCTS solver with some of the parameters. And I recommend using the built-in documentation within Pluto, so you can see, what are some of the parameters and, what do they do and how are they controlled. And then we solve this. And as I mentioned, or rather I failed to mention, when we solve an online solver, we're actually not doing any work, which is why we call it a planner here. It's a little pedantic and set up a policy, but really this indicates that we're just planning on what to do, and then when we actually query the policy for an action, or rather the planner for an action, that's when the work is actually done. So we'll pick some random state here. You can also just sample from the initial state function, given that MDP. And similar to the action function from above, MCTS provides this action info function, which gives us a little bit more information that we can use. And this is what's actually going to do the heavy lifting. MCTS also has a computation clock parameter that you can control so it doesn't run on forever, and it just stops and says, okay, what is the best action I've found so far, given your root node state? So we can visualize the tree that Monte Carlo tree search produces using D3 trees. We can define, some of the formatting for the tags here, and this is just kind of the helper function for us. So we have this tree, which we'll call from that tree info. Given our initial state of 8.2, we can see the colors of these actions down here indicate their discounted future reward. And the thickness of this indicates how many times the algorithm actually traveled down that path to see if there was more reward it could get in the future. And so what we can look at here is, well, let's go down, 8.2 is near that maximum reward state of 9.3. So if we went up, right, there's 4 states we could transition to here. We could go to 8.3, which is the most likely. That's the one that actually provides that up functionality. Or we could transition to the ones around it. And you can see the algorithm is really focusing on this part of its future. If we follow this down, we can see, okay, from here, if we take action right, our Q value is 9.27. And that's why this is indicated as green. And this is actually that terminal state. So from here, we transition to the state 9.3, which actually gives us a reward of 10. In all of these other cases, there hasn't been any reward we've gotten yet. We can only look at the Q values, which is that, discounted reward that we would get in the future that's spread up through here. So you can kind of see how the Q values change from 10, and then we use the discount, and the transition probability affects this value, and then, affects this value to 7, and so forth. And so from here, we'd see, okay, no matter what action we take, we still get that reward of 10, and then we transition to the null state. So this is what's happening at a particular state. But the thing is, what MCTS is doing is, rather the way you use this is just from a current state, what's the next action? Transition to, whatever actually happened in the environment. Again, everything down here is simulated, or sometimes called hallucinated. And so you would recompute it given whatever, actual state you transitioned in, and you would rebuild this tree. Next, we'll talk about how to run simulations, and we'll use the POMDP simulators package for this. And so the simulate function, which takes the following signature, takes in some simulator, which we'll define here, our problem, our MDP, and the policy, and some initial state potentially. So there's several different types of simulators you can use. I refer to the docs for a little bit more details. But one way, if you want to just run fast simulations and get some discounted rewards, you can run a rollout simulator, which we'll use later. If you want to closely examine those histories of the states, the actions, the rewards, the next states, then you can use a history recorder. If you want to visualize a simulation in things like Electron or Pluto notebooks that pop out a different window, you can use the display simulator. If you want to run many different Monte Carlo simulations just across parallelized across many different threads, you can use the run parallel function that takes in some sim objects of a bunch of different a bunch of different objects that would be thrown onto different workers. If you want to interact with the simulation environment from the perspective of the policy, then you can use this sim function. And then lastly, if you want to step through each individual simulation step, you call the step through function. You give it the problem, a policy, what types of outputs you want to see, in this case, the state action reward and maximum number of steps. As an example, we use the with terminal function. This is a Pluto UI function, so we can actually print out in here. But we say, okay, so step through the MDP, which will randomly start at some random initial state, and give me back the state action rewards, and we'll just loop over those in a for loop for state action reward. And I'm just going to print out, okay, I'm in state S, I take action R, or rather write that's from this policy, and what reward they receive is 0. And so you can see as we step through this, it's going to actually play out or simulate the agent in the environment. And we can see, okay, at the end, we finally, go into state 9.3, take action F and receive the reward 10, and the game is over. You can also collect those values from step through. And so you can see this is an array of tuples, named tuples that have a state, action, and reward, S, A, and R. You can see all of the different steps here. And what's nice about that is we can actually play through what happens to an agent actually walking through this environment and playing through. What you might see is sometimes it won't actually follow the action that is prescribed in that cell itself, and that's because of the transition probability. So here we want to go right, we go down, we go down, we go right, down. Oh, well, there was a 10% chance we would have popped back up, and we did. And so we keep going, and eventually we land in the terminal state here, and we collect that reward, and this particular simulation is over. We can also animate a full simulation just like I did, but save it out to a GIF so you can see this. There's code here to show you how to animate it. And this way you can kind of play through a simulation and save off some cool animations. Another simulator that I'll go into a little bit of detail here is a rollout simulator. And so for each of the algorithms above, I'm going to run 10,000 different random initializations that just run through a single episode. In this case, an episode just follows the policy until it hits a terminal state, starting from some random initial state. So this rollout simulator will return the discounted reward, or sometimes called discounted return, that the agent collected, meaning in this particular grid world problem, the final reward is discounted based on the chosen gamma, where you can see here that that discounted reward, is the sum of all time steps to the horizon or the end of the problem, where we discount the given reward based on the time, and we collect the reward from that particular state. And so as an example, if our first state is time step t equals 1, this moves into a reward state, which are actually terminal states in our grid world definition, and we would directly return that reward value because gamma of 0, or rather gamma raised to the 0 is equal to 1, so we just return that value. And you can see as we simulate it a bunch of times, we're going to run a rollout simulator given our MDP and policy, and we can collect random rewards. And sometimes these will be potentially the negative reward because that was the first thing we transitioned to. Other times, like right there is -10. Other times, it's some kind of discounted spread, which is noticeable in these real values here. So now we'll run 10,000 number of simulations, each representing a single episode, and collect some reward statistics here. So this is going to run it for all 3 policies, both value iteration, Q-learning, and SARSA, and then it's going to plot what is the mean and the standard deviations of these rewards. You can see value iteration tends to be the best, or is the best algorithm here because, as I mentioned, it's actually getting the optimal policy, whereas the other 2 are using reinforcement learning to interact with the environment and get some approximately optimal policy. And just very lastly, just briefly touch upon, the code down here will show using some color maps that I've defined using the color schemes and colors packages, and some kind of nice shout out to Nicholas Korbsbo about this LaTeXify package, which is just kind of a clever way to turn Julia expressions into nice LaTeX formulas, which I think are useful for teaching like this. And then at the bottom here, we'll have references that are listed above. And next, we'll talk about POMDPs and dive into a POMDP problem. Thank you for listening.